Test, test, test. Hello, hello. Testing, testing. Can you? I'm sorry. Unique New York. Unique New York. Can you log into the live stream on your or access the live stream on your phone or something? See if you get audio. Streaming. Soon, early. Is that right now?
No.
Unique New York. Unique New York. Okay. So. In the booth, I'm going to try splitting the HDMI signal going into BB2. Just FYI, I hope I don't break anything. But you're going to lose it for a second. Am I looking at the wide shot? I probably am. Can you show me the tight shot? Yeah, lift the camera a little bit so we see the whole Flat screen. Yeah, that's better. Thanks. Did you get the feedback from BB2? Go to the monitors, or did we just lose it altogether? Sounds like we lost it. Hold on. Okay, well, there it is, back. Fantastic. Okay, so you now have the capability of showing the board exclusively, or so so now you've become the director. You get to switch.
Okay.
We may never. Well, one of us will have to remember. Good morning, everybody. Welcome. We see our size shrinking as we expect. It's 8 o'clock in the morning. People, if this isn't your first college class at 8 in the morning, you'll understand that your colleagues will be still in bed. There's actually a live stream as well, as you know, so you can watch it from your bed if you'd like to. We will, the poll everywhere, your attendance credit is not for watching the live stream, so you can respond poll everywhere from the live stream, and we'll record your responses will be may be recorded. We're actually going to try to do it so you can respond, but they're not recorded. But we won't count them if they come from the live stream as opposed to in the room. So the attendance, short story is the attendance credit is for being in the room. And it's not that and it's not because we're trying to get the population in the room high. In the room, you talk to people. The attendance credit is not for coming. The attendance credit is for doing the chem quizzes and doing the peer instruction with your peers. So that's why we do it, not to just put butts in the seats. As you know, attendance is not required at all. You don't have to come, and the attendance credit is bonus. It's not even part, it's just extra credit. It's not part of the course. You can get all the course points without attendance. So it's just so we encourage the kind of peer learning and peer instruction that we're getting here, and being all friendly and one group. I think that's it. So we'll talk about the little midterm tomorrow in a second. We'll get to that. As you know, learning goals and where are we now? We're talking about amounts of matter. So we're trying to correlate, basically we're trying to correlate macroscopic amounts of matter with microscopic amounts of matter. That's not clear yet because we're using macroscopic matter. We're using rocks, papers, and scissors as our demonstrations, but you know, I can't hold up a carbon atom, so it works either way. So, but here's a cautionary tale. So what is this? This is the results from a real exam we gave in Chem 1, where the question was the most accurate value of the standard enthalpy of formation of ethanol gas that can be calculated from the table. So in this question, there was a table, and you use the data from the table to calculate an answer. But as you probably know, there's this thing called the internet. Has anybody use that? So you could also Google enthalpy of formation of ethanol, couldn't you? And a number would come up. And you know what number would come up? This one. But that's not the answer you would get if you did it from the table like you're supposed to. Okay? We know the internet exists, and we know you'll be tempted to use it. Do not do it. It will screw you up. So only, and it's outrageous. Almost half the people just Googled it. That's shameful. Remember, we're taking this class with the ultimate in academic integrity. We give you the exams online. It gives us freedom to give the exams whenever we want. It gives us more time in the classroom, but we expect that you use the information on the exam and the information on your equation sheet that is posted with the exam, and nothing else. The software as well, the B course, the Canvas software, can tell when you switch windows or are not, if you're opening tabs and stuff like that on your browser. So it is also watching you like Big Brother. So please, for your own good, use the stuff we give you and don't use anything else. the exam will only cover what we get through today, obviously. We're not exactly in sync with the syllabus, so we won't get to phases and forms of matter probably today. So it will only cover up to what we do today. The homework, as you know, sometimes covers, one homework might cover a couple lectures. So if you're doing homework, you might be seeing questions. You'll often see a question that we haven't quite got to yet, especially if you're very current on the homework, because we might be behind in the lecture, so you might not have seen it yet. It's all covered in the reading associated with the lecture, so you can do the reading in advance or use the reading to do the homework, but you might see stuff a little far in advance. But we give you the learning goals, so the next set of learning goals that I show are the only learning goals that are associated. You'll have seen all learning goals associated with the exam today, and like I said, we won't get to phases of matter. So last time we were here and we talked about masses of things, and you guys surprisingly struggled a little with this. All we wanted to do was take 300 pounds of rocks and put it in a box, and then put equal masses of paper and scissors in a box. So 300 pounds of those and 300 pounds of those. That's all we wanted to do. This brings up a couple things. A lot of times people overthink the question, or maybe you think that I'm trying to trick you, or there's a trick to it, or there's something more sophisticated there. The answer is no, that will never happen. I never try to write trick questions. I always tell you exactly what I want you to tell me, and there's not a trick in them. There's not something that is clever or will get you the wrong answer if you think the wrong thing. But even if I say that, you still remember, we do speak slightly different languages. I speak very, very, very precisely, and you already know I use a word one way and you might not use it exactly the same way. So you may interpret things, you might not interpret them because of the language barrier correctly, but at no point are we trying to trick or confuse you. And even on multiple choice questions that require a number, I put the right number down and all the rest are garbage. I don't try to say, oh, well, what if they forgot a factor of 2 or something like that. So if you see the right answer and you mark it, you got it. It's not like you could have made a mistake somewhere. So we are not trying to trick you or catch you because you made an error. We're trying to help you get it. So if you think you did it right and you don't see the right number, then you probably made a mistake. It's not like you should go back and check the math, because maybe you are off by a factor of 2, but that won't show up in an answer. So if we did equal masses, it would be obvious. We would take 300 pounds of rock, and then we would put on top of that 300 pounds of scissors and 300 pounds of paper, and the whole thing would weigh 900 pounds at the end. That's not overly, that's not a stretch, and it wasn't a trick or anything. So don't overthink it, and use only the information that's there. We try to give you, what you need in the question, and if you start thinking about 100 different scenarios, then you get yourself into trouble. So I try to write the questions as simply as possible, and you should try to interpret them as simply as possible. So the other option is, let's put equal numbers in the box. So we put 300 pounds of rocks, but we don't know how many individual rocks there are. But we want to somehow make a scissor for every rock and a paper for every rock and scissors. So there's an equal number of scissors, papers, and rocks in there. And all we know is what's left in stock, and we know the relative masses. We know that the rocks are 3 times the mass, 3 times as heavy as the scissors, and the paper is 1/10 the mass of a scissor, so 1/30th of the mass. It would take 30 pieces of paper to give you a rock. It would take 3 scissors to give you a rock. If I know that, can I put equal numbers? I go to the hardware store, they put 300 pounds of rocks in, and I say, okay, all I can do is weigh them out. I have a scale, I can't count them. I just have to put a mass of scissors on the scale and weigh out enough that the numbers are equal. Is that even possible? So talk about that amongst yourselves. GSIs, you may rise and talk to the class, and we'll see what you're thinking. What do you guys think? I'm sorry?
So there's 300 pounds of rock. One rock weighs 3.
You can say that. Yeah, I mean, you can say it. It doesn't. You don't know if it weighs 3 things, but if it did weigh 3 grams, then a scissor would weigh 1 gram. You can say that because you know the relative masses. Yeah, you don't know how actually much they weigh, but you just know relative to each other. So if you put, let's do the very simplest way. If you put, say it weighed 3 grams. If you put 3 grams of rock in there, you would have only put 1 rock. Well, how would you get 1 scissor? You'd put 1 gram of scissor. So multiply that by 100. You put 300 pounds of rocks in. How many pounds of scissors? Oh my God, it's trivial, isn't it? This one you have to do slightly more math, but. Oh, I'm sorry.
No, you're okay.
In this case, if you had the same number of rocks, you have
Yeah, exactly.
now you have to.
Okay, we're getting near the end of the discussion. I hear it tailing off. Let's see what you're thinking. We'll look at the responses. We're all over the place. We have a lot of A's. We have quite a few C's, and I understand people's D saying that's not enough information to do that. So is it enough information to do that? Well, I don't know how much a rock weighs, and I don't know how much a piece of scissors, 1 scissors weigh, and I don't know how much a piece of paper weighs. I don't know their mass. I'm not going to use that term weigh very often, weight. I'm going to use the term mass. That's the more precise term for this. So when I say mass, if you think weigh is a better, how much it weighs is a better term, just translate on your own. But I'm going to put a mass here that I know into the of rocks. I don't know how much an individual rock weighs, but I know their relative masses. So it's actually, you could say, well, every rock weighs 3 times a scissor. So let's just say a rock weighed 3 grams. Just say that, we don't know. But if it did, how much would 1 scissor weigh? 1 gram. So that's easy. I can make them 1 to 1 if there's 1 of them. But it works for any mass. So if 3 grams match with 1 gram and you have the same number, if you multiply and say 300 grams, how many scissors do you need? 100 grams of scissors will have the same number of scissors as rocks. And it could be pounds. It doesn't matter. If you had 3 pounds of rocks, and that was 1 rock, then 1 scissor would weigh 1 pound. And you would put 3 pounds of rock, that would give you 1 rock, and then you'd weigh out a pound of scissor, but it's 1 scissor, so it's not too mysterious, and you'd put it in the box. But when you go to big numbers and you don't have time to count out all the rocks, you say 300 pounds of rocks, I don't even know how many it is, I don't even care how many it is. But I do want to make sure I have a scissor for every rock, because we're going to play rock, paper, scissors later. So put 100 pounds of scissors in, and then I'll have a scissor for every rock. And then the paper weighs 1/10 of the scissors. So if 100 pounds of scissors was in there, I need 10 pounds of paper. We'll have the same number of pieces of paper for every scissor that's in there. So I don't need to know how much they weigh, and that's handy. Because sometimes you don't know the exact mass of one thing, or it's hard to find. But if you know how much it weighs, what its mass is relative to something else, if you know the relative mass, you can arrange to get the same number of pieces in the box with a scale instead of with a balance, by mass instead of by counting them out. And you can imagine, when you get up to 300 pounds of rocks, that's a tons of rocks, you don't want to count the scissors into the pile, do you? You want to just weigh a bunch of scissors and drop them in. That's easier. So that's how the hardware store works. So 1/3 the mass, and the mass unit doesn't matter. Pounds, kilograms, tons, stone is a unit of mass. Any unit of mass you can put in there, because it's just relative mass. It's a multiplicative factor. It doesn't have anything to do with changing the mass. So if you did that, you'd have a box that weighed about 400 pounds. Fantastic. So you could go, here's just a summary of that. You could go to the hardware store, and the hardware store might have a table like this on the wall, so you can do that. You can say, I want a bolt and a washer combination. Give me 200 pounds of bolts, and I need 1/6 of that. So I need 6 goes into 200, 6 goes into 20, 18, 3-ish times 3 and a little more pounds of washers. And I would have a washer for every bolt. Oh, it's easy to do it bolts to nuts. Give me 2 pounds of bolts and a 1/2 pound of nuts, and I'll have the same number of nuts and bolts. So easy when you're at the hardware store, especially if you're going to make a whole building. So it's true for any mass unit if you're just using relative masses. So this is a table of relative masses. It doesn't matter what the mass unit is. That's handy. Could be grams, kilograms. It's true for if they come in boxes. It's especially true. If they come in boxes of 100, then the boxes will all have the relative mass relationship, right? Because that is the right number of, that is a matching number. If I say a box of 100 bolts, it'll weigh 2 pounds. Then a box of 100 nuts weighs half that, 1 pound. It's neat with they're in boxes because you get the right number immediately, but you would also know how much they weigh relative to each other, because same number of particles, same number of pieces will have the relative mass relationship between them. As long as the number of pieces are the same, you can apply the relative mass to go backwards and forwards. Pretty simple. Okay? So that's just a summary of that. So let's see if you can do it. You're gonna build an entire building, and you need 1.5 metric tons of bolts. And you've got to make this combination all over the place. You have to put a nut and a bolt and 2 washers together. So you need to buy enough washers for your bolts, and you're going to buy 1.5 metric tons of bolts. how many metric tons of washers do you need to have 2 washers for every bolt? GSIs, let's talk about it with everybody. Excuse me, I want to go down and talk to these people in the middle. What do you guys think? Have you voted yet, or got it? Oops, not everybody has to hear. Yeah, guys. Sorry, let me put the relative masses back up there for you. I forgot to do that. I thought you have the slides, right? You have them physically. Does anybody need to see the? I'll put it up there. We don't have to look at this. You all have the question on your phone. But if you want that table, you do need this table to do it. Where were those people? Okay, let's see what you are thinking after that calculation. I'm sorry, I kind of assume you come with this information printed out, and if you don't, just online, they're sitting there on the website. You can look at them, but I can change what's on different screens, and I can do that next time. So we were thinking about this, and I think the voting was on. So let's see what you were voting. I hope I didn't restart it by doing that. Oh, okay. So many people are thinking that last answer there, that's the most popular. The last answer there is a quarter of a metric ton is what you're saying. So let's go through it together. So this is what we need to do. We need to make this connection. We need to make this thing, our connector is a bolt, a nut, and 2 washers. Okay? So how do we make that? Well, if I take one relative mass of bolts, and whatever mass unit this is, it doesn't matter, right? This could be pound, gram, ton, okay? So 1 mass of that would have, and 1 mass of nuts, and 2 masses of washers. I'm sorry, I said that wrong. I need 1 relative mass of bolts, 1 relative mass of nuts, and 2 relative masses of washers. Let me do one more step and that'll be more obvious. So the relative masses are 2, 1/2, and 1/6. So now the units don't matter. So the relative masses, if this can be grams or tons or ounces. So 2 tons of bolts has the same number of bolts as 1/2 ton of nuts and 1/6 of a ton of washers. So that would be equal particles, equal numbers of stuff, and the unit doesn't matter, any unit. They'll have equal numbers. That's the same number of nuts, bolts, and washers. Okay? Get that from the relative masses. One relative mass of something has the same number of particles as the relative mass of something else. So a relative mass of 2 has the same number of particles as a relative mass of 1/2, has the same number of particles as a relative mass 1/6 of that. So we'll adjust for the actual masses. We didn't have 2 metric tons. We had 1/2 metric ton. So I'm just going to multiply through by 1/2 over 2 to change that to 1/2 metric ton. Now I have 1/2 metric ton, and I have to do that for everybody. So I have a 1/12 of 1.5 metric tons there. But then I have to realize I do need 2 washers for every nut. This is 1 to 1 to 1. I need 2 washers, but that's just twice the mass, right? Just weigh out twice the mass, and you'll have 2 of those. So I can just multiply that mass by 2. And I'll have 3/12 of a metric ton there. And now I have 1. Sorry, I went back to. Where did I do the 1.5? Did I multiply? I multiplied everything through by 2. What did I do that for? Oh, I see. These are still 1 to 1. If this were 2, these would still be 1 to 1. But that's not helpful. This should be 1.5. This is 3/12 of a metric ton. That's 1.5 times 2 over 12. 3/12 of a metric ton is what we need. And 3/12 is 1/4. So we need 1/4 of a metric ton there. Go back and change those numbers. These numbers should have just come straight down. Oh, I know what I did. I did a copy and paste, and then I didn't change the first 2. Okay, so it's easy to track. What I always do is just get equal numbers of everything, because that's easy. It's just you just put the relative masses. This relative mass is 2. That relative mass is 1/2. So that'll give you the same number of particles. 2 tons of that, 1/2 a ton of that, same number of particles. And then if you need different numbers, just take more mass. Multiply the mass up. Here's a different way to think about it. We can just do that in discussion. So here's our hardware store list again. Our staples and our paper and all the stuff we can buy at a hardware store. What I'm going to do is multiply through so they're not all fractions. I just want to get easier numbers to work with. So I just multiplied through the table to get rid of all those fractions. So it's a little easier to look at. And you can do that. It doesn't matter. As long as the ratios are the same, it doesn't matter what your base number is. Multiplied them all through and got a, it looks like I multiplied them all through by, this was the lightest one. So I just multiplied through by 12 everywhere. Multiplied everything through by 12 just to get rid of that 1/12 and get rid of some of the fractions there. Okay? That's easy enough to do. And sometimes if you go to the hardware store all the time, you'll just have abbreviations for all these things. So scissors, a paper, a clip, a washer, a nut, scissor, a bolt, rock. Crushed rock. CR. So all I've done is arrange everything in order of increasing relative mass. Okay? And I gave them funny symbols for short. Does that remind you of anything? What does it remind you of? Reminds you of that thing, doesn't it? That's a bunch of funny symbols arranged by increasing relative mass. That's what the periodic table is. So here's the periodic table, and I'm just arranging by increasing relative mass. This small number down below is the relative mass. So 1, 4, 6.9, 9, 10, 12, 14, 15, 16, 19. It's just increasing relative mass. And that is super handy, right? Because now you know how to combine, it's just like the hardware store. You can combine any number of oxygen particles with the same number of hydrogen particles, can't you? Because you know their relative masses. And that's handy because you can't count out. You can never count out the particles individually. They're too small. And in fact, you don't even care how many particles there are. Who cares how many individual particles there are? You want a gram of carbon. I don't care how many particles there are, but I want the same number of particles of hydrogen, so I take a relative mass of each of them. And it doesn't matter the unit. I can take a pound of this and a relative mass in pounds of that, or grams or ounces, and I'll have the same number of particles. That's fantastic. That's what I need, because I can't weigh the mass of an individual one. In fact, I don't even know the mass of an individual one. Don't need to know the individual mass, don't need to know how many are there. Very handy for tiny things, right? Don't want to count them all out, and I don't want to know a tiny, 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 tiny mass. I want to know relative to other things, and that gets rid of all that icky stuff. Okay? So that's why we arrange the periodic table like this. Relative masses. You can go and say, if I need to take hydrogen and oxygen and mix them together, if it's going to be 1-to-1, 1 gram of hydrogen and 16 grams of oxygen would do that. If I want it to be 2-to-1, what do I do? 2 hydrogens to an oxygen. 2 grams of hydrogen with 16 grams of oxygen. Right? And I have the right number of particles. Easy. What?
Not 32 instead of 16.
I want 2 hydrogens for every oxygen. 1 oxygen, 1 relative mass of oxygen, 16 grams, 2 relative masses of hydrogen, 2 grams. That's 2 hydrogens and 1 oxygen. Okay? That's water. So the relative mass of water is 2 plus 16, because it has 2 hydrogens and an oxygen. So the relative mass of water is 18. That's handy. So I can do it for molecules too. Just add up the relative masses of the particles in there. Okay? This is bugging some of you guys, isn't it? I've never said the word mole. I never said the freaking word mole yet, have I? You don't need it. It's a freaking... look, you want to go be ambassadors of science. Does 6.02 times 10 to the 23rd help you talk to anyone? You don't care. I don't care. It's such a stupid number. 6.02 times 23 is a astronomically huge number, and it doesn't matter. You don't care the number of particles are in there. You weigh it out on the... You want 18 grams. You don't care how many particles are there. So, that's just a little sermon for you. So here it is. Here's part of the periodic table. And I have the relative masses here. And for the periodic table, we actually, you know how I multiplied through when I did it in the hardware store? So I had 1 base unit. We kind of do that. We use carbon as the base unit on the periodic table. But here are some relative masses, and we just calculated what that relative mass would be. So those are all there. These numbers, here's something that we'll talk about a little bit. This number is 12. If you take 12 grams of carbon-12, and that would be some number of particles. If you take 1 gram of hydrogen, that would be 1 for 1. If you take 12 grams of hydrogen and 12 grams of carbon, then you'd have 12 hydrogens for every carbon. But notice this number. This is the number that appears on the periodic table, not these .00, not these exact numbers. This number appears on the periodic table for an interesting reason that we'll talk about in the next slide. It turns out there's different kinds of carbon, different flavors of carbon, and the different flavors of carbon have different relative masses. It's just a pain. They're out there. They're out there in nature. There isn't much. Most of the carbon in nature is this. It has relative mass 12, but there's, for every 100 of these, there's 1 of these out there in nature. So this fraction here accounts for, if you took natural carbon, it's a mixture of these two things. There's 100 of those, there's 1 for every 100 of those. And then there's also an even more massive carbon. There's more massive carbon, but there's hardly any of that. So it hardly shows up. But that's the origin of these, kind of fractional numbers, because the relative masses on that periodic table represent a mixture of the different kinds of carbon. And the different kinds of carbon are called isotopes. If you have the same element but a different mass, that's an isotope of carbon. So carbon-13 has mass 13, carbon-14 has mass 14, relative mass 14, and but it's still carbon, it's just slightly more massive. And we can look at the individual atoms, but in general, it's not worth doing. But here are individual cobalt atoms arranged on a copper surface. Here's some nickel atoms, and you see this little bulge. That's what the microscope detects. It detects that there are cobalt atoms there. Here's some molecules of cesium iodide, and here's some xenon atoms on copper. And those clever guys at IBM, they detected the atoms by bumping into them. So when they bumped them into them on the surface, they said, oh, there's an atom there. But they found that they could bump into them hard enough to push them around. So they pushed them around to spell out IBM with xenon atoms on copper. We're going to do this in discussion, but we'll do it now. And again, this is kind of review for 99% of you. But since we have an exam tomorrow, I'll do it. I'll go through it. What do those individual atoms look like? And what's the origin of that different masses? How come you can have a different mass and still be the same element? So I think you know, atoms are composed of a positively charged nucleus and negatively charged electrons around that. And we talked about that, why that is. Those electrons are trapped in the potential well of the positive charge around the nucleus. I say trapped because they don't have enough kinetic energy to get out of the well. Their kinetic energy is less than the potential energy that they have around that nucleus. So they could zip up the wall, but unlike Chloe Kim, they don't get out of the half pipe. They are stuck there. They don't have enough kinetic energy to get out. So they're trapped in that well around there. So we have Z positive charges. This is a number. Z can be 10. Z negative charges would give you a neutral atom. So positive charges in the nucleus balanced by negative charges outside. The charge is the charge on an electron. So if I have 10 negative charges, that means I have 10 electrons. All of the mass of the atom is actually in the nucleus. the electrons weigh like a 2,000th of a nuclear particle. So most of the mass is right in the center. And this is mostly empty space where the electrons are, because the electrons are tiny and they're flying around the nucleus, but they're itty bitty. The atom is pretty big, so most of it is empty space. In fact, and it's huge. If you took, if the nucleus of a carbon atom were the size of a pea, you blew it all the way up to the size of a pea, then this dimension out to the edge of the atom, out to the edge of the electrons, if you put that pea in Memorial Stadium, where the Cal Bears play, if you put the pea in the middle, the electrons, the farthest electrons would be in the cheap nosebleed seats. And all that is basically empty space. There's a few electrons in there. If it's carbon, there's 12 electrons flying around Memorial Stadium. There's not much chance you're ever going to encounter one of them. All the mass is down there on the field in the nucleus. So Z is called the atomic number, and the atomic number is the number of protons in the nucleus. Protons are the positively charged nuclear particle, and I think you know all this. Protons are positively charged. The number of protons in the nucleus is balanced in a neutral atom by the number of electrons outside. This is the atomic mass. That's the 14 I had there above carbon. And the atomic mass is the number of protons plus the number of neutrons in the nucleus. So there's two particles in the nucleus, protons and neutrons. They have the same mass essentially, but the protons are charged. Okay? So the number of protons, Z, the atomic number, determines the element. That's the only thing that determines the element. Not the number of electrons, not the number of neutrons. If you have, we go to the periodic table, if you have 6 protons, carbon is atomic number 6. If there are 6 protons in your nucleus, you are carbon, regardless of how many electrons or neutrons there are in your nucleus. If you take nothing else home from Chem 1A, take home the fact that it's only the number of protons in the nucleus that determines the element. None of that other stuff. That's all extraneous stuff. But now that leads up to, how can you have carbon with different masses? It has to have 6 protons, but it can have a different number of neutrons that also have a mass 1. So if you have a carbon of mass 12, it has 6 protons and 6 neutrons. That gets it a mass 12. But it could also have 6 protons and 7 neutrons. And then it would have a mass 13. 6 protons and 8 neutrons. Still carbon, more massive, but it would have 2 extra neutrons in the nucleus. Okay? In fact, I'll just show you this. We'll just go back and just make a point of it. We give these things symbols. Those are the symbols up there. And now you can see they're arranged by not only relative mass, they're arranged by atomic number. 1, 2, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Those are increasing by 1 proton as you go. Okay? They're increasing by a number of neutrons, but that isn't constant. That's an average of all the different isotopes in nature. So we don't expect you to memorize those symbols, but the symbols are there. Once you know the symbol, though, these two things are the same information. The atomic number and the symbol are the same information. If atomic number is 6, it's carbon, no matter what. Number of protons is the only thing that determines the element. So you don't need this one in general. So sometimes we don't write this one. This mass, you do need to know. It's the relative mass. That's the important one. That's how you figure out how to get the same number of carbons as hydrogens. You need that one. And this one is an average of all the isotopes. If it's all carbon 13, then it's exactly carbon 13. But if it's a mixture of carbon 12s, 100 carbon 12s for every 1 carbon 13, then the relative mass is 12.01. in your sample. Okay? You don't have to memorize elements and symbols. In this class, I don't want you to memorize anything. We're going to give you an equation sheet that has all the equations. We're going to give you all the constants. No memorizing anything, including the symbols. I don't care if you know those symbols. When I took Chem 1 at Michigan State many years ago, my professor, Dr. Spies, he was lazy, I guess is the only word for it. On the exam, he would put a blank periodic table and we had to put in the frickin' elements by letter. Does that make you an ambassador of science if you can do that? No, it does not. So what I did is I just memorized them phonetically. I would just spit them out in order. Ha he, libi basi nafni, namgal subskarteka. And I would just be able to just phonetically say them all at once and just put them into the boxes. What good has that ever done me? You will not have to do that. That is not how we teach chemistry. We want you to have conceptual knowledge and be an ambassador of science. So, what relative mass of sulfur is required to react completely with 1 gram of oxygen? So in the interest of time, I'm going to start going through these because we have an exam on Friday. So rather than do the votes, we'll talk through it. It's not as good. You don't get as good a recall. And talking is important. Two easy reasons talking is important. One, your cognitive side and your talking side of your brain are on different sides of your brain. So the cognitive science people kind of say, well, you can know it, but if you say it, that gets some more neurons involved. So saying is important. So say stuff out loud, even when you're studying. Just say the concept to yourself out loud, not in your head. Say it out loud. Talk to the mirror. Better, talk to somebody next to you. That's even better. Okay? You do not understand something. What's the litmus test for being able to understand something? Many of you think you understand things. Exactly. If you can explain it to someone else, then you understand it. And you've probably seen already, just talking to your neighbors, you say, oh yeah, I did that in AP Chem, I can explain it. But you'll get, about a third of the way through and you'll go, oh crap. You stumble on where your conceptual gap is. And you overcome that means you understand it. That's why we do this. Talk to each other. And when you study together. Explain a problem to your colleagues. That is what gets you going. When people come to office hours, I make them talk. That'll probably keep you out of office hours. You have to talk through it in office hours. I'm very supportive. I love you guys. So, relative masses. Here we're gonna get what mass of sulfur is required to react completely with 1 gram of oxygen. We already did this with nuts and bolts and washers. It's easy to do. 1 gram of oxygen. Here are the relative masses. 16 grams of oxygen has the same number of particles as 32 grams of sulfur. That's the same number of particles. So I have only 1 gram. But I can see that that's 2 to 1, right? So 1 gram of oxygen has the same number of particles as 2 grams of sulfur. Pretty easy. Are we done already? 2. Yeah, that was easy. Not going to vote on it. You can vote on it if you want. You don't have to vote on it. We're going to just blow by that. The relative masses are 32 to 16. I'm sorry, we had oxygen molecules. I did one sulfur to 1 oxygen, but we need 1 sulfur to 2 oxygens. So that's the same relative mass. That makes it even easier. So 1 gram of sulfur has the same number of particles as 1 gram of O2 molecules. They have the same relative mass. So super easy. 1 gram of oxygen has the same number of particles as a gram of sulfur. 1 pound of oxygen molecules has the same number of particles as a pound of sulfur atoms. Pretty easy to do. Just apply those relative masses. And again, what I always try to do, get the equal numbers, and then you just account for whether it's a molecule or whether you need 2 or 3, and just multiply the relative mass up to get what you want. Okay. I said we'd do this in discussion, but let's do it now so we can talk about it. What mass of methane is required to react completely with 4 grams of oxygen? Like this. This is methane, CH4. And again, on the exam, we would not just say methane. In the question would be CH4. So you don't have to know that. Oxygen, we would say oxygen, O2. So you don't even have to know that. This is carbon dioxide and water. So these two things reacting to each other. What mass of methane? 4 grams of oxygen. Let's just go through it. Don't have to vote. The relative masses. Carbon 12 relative mass. Hydrogen relative mass 1. So 12 plus 1, 2, 3, 4 hydrogens. The relative mass of the methane is 16. Relative mass of oxygen is 16, but we have 2 of them. So there's a relative mass 32. And that ratio is, that's handy, it's 2 to 1. So the relative masses are 2 to 1. So in every 2 grams of oxygen has the same number of particles as 1 gram of methane. 32 grams of oxygen, 32 pounds of oxygen has the same number of particles as 16 pounds of methane. So it makes it easy. 1, whatever the heck you want, ton, blah, 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 blah. 1 ton gram of methane has the same number of particles as 2 pounds, tons, or grams, because that ratio is 2 to 1. I mean, you could put 16 in there. 16 pounds has the same number of particles as 32 pounds. But all you've done is multiplied through by 16. Or you can look at it, I have 4 grams of oxygen has the same number of particles as 2 grams of methane, because the relative masses are 2 to 1. That's the same number of particles. But we need 2, just like the bolt and the 2 washers. We have to have 2 particles of oxygen for every particle of methane. So 1 gram of methane reacts with 4 grams of oxygen. That's 1 relative mass. That's 2 relative masses. And the number of particles will be 1 to 2 as well. If you have a ratio of relative masses, you have a ratio of particles. Easily done. So it takes a gram of methane, and you use up all your oxygen. That's nice. I say you could also do this 16 and 32 if you want, but that's just 2 to 1, so doesn't matter. It's all relative. This one's slightly different. What mass of carbon dioxide is produced when 1 gram of methane reacts with 2 grams of oxygen? So now a gram of methane is going to react with 2 grams of oxygen. So this brings up just another concept. There's some relative masses. Again, 1 to 2 to about 3. This is approximate. That's about 3 to 1. Oops. So 1 gram of methane, we already found, reacts completely with 4 grams of oxygen, because that's 1 relative mass, and that's 2 relative masses of oxygen molecules. That reacts completely. Half a gram of methane reacts with half that many oxygen particles. Half a gram. So half a gram is left over. If there's only 2 grams of oxygen total, it can only react with half a gram of methane. This is, these particles are arranged 2 to 1. There's twice as many particles here as here, but you run out of oxygen, and you have a ½ gram of methane left over. So if you start with 1 gram and 2 grams, 1 and 2 don't go together very well. 2 goes with 1/2. I had ½ gram of methane. I use up half of it. And all my oxygen is used up. ½ gram of methane is left over. So this thing, oxygen limits how far the reaction can go. You run out of oxygen particles. So oxygen is called the limiting reactant or the limiting reagent. None is left over. The methane is in excess. There's still some methane left in the flask. So in the flask, when you're done, you have ½ gram of methane, all the oxygen's gone, and you have some carbon dioxide and water. And we know this ratio of relative masses. So if a ½ gram of the methane actually reacts, you get 1 relative mass of carbon dioxide for every relative mass of methane. So if their relative masses are 3 to 1, then you have ½ gram of methane left. That means it would produce 3 times the mass, 1-for-1 particles, 3 times the mass of carbon dioxide. So you can see it produces carbon dioxide. And you can use the relative masses anywhere you want. Products, reactants. 1 relative mass of methane would give you 1 relative mass of carbon dioxide. The relative mass is 3 times this. So you have 3 grams of, or 1.5 grams of carbon dioxide. What is this, same thing? The question, all those numbers are correct. I think the question was how much, I don't remember what the question was. The question was what mass of carbon dioxide is produced. So we have to get to when 2 grams, is that what the question was? So we have to get to 1.5, yeah, we have to get the mass of carbon dioxide. So we have to get to the mass of carbon dioxide. I'm not sure why we've circled 1 there. Yes, this is the answer we were trying to get to. So we'll just do the whole mass balance. 1 gram of methane, 2 grams of oxygen. That produces ½ gram of methane and about 1.5 grams of carbon dioxide. Those things react together. All that gets used up. You have half of it left over, half the mass left over. And that ½ gram that reacted produces 1.5 grams of carbon dioxide. Half a relative mass, 1.5 or 0.5 there, gives you 1.5 grams there. So again, I think this is just on the wrong spot. It would also produce around 1 gram of H2O. Why would it produce about a gram of, it would produce around ½ gram, produce about 1 gram of H2O. Because every relative mass, if 1 gram of this reacts, the relative masses are about the same. Water is 18, methane is 16. So 1 mass of that would always produce 2 masses of that. So 1 gram of this would produce 2 grams of that. And we're going to react ½ gram, so we get half that 1 gram of water. All the masses should add up in the end. We'll do that in a minute. Okay, so we went through those so we could have enough material to be on the exam. So let's just continue with the next bit. Maybe before I forget, I should take this and move it over there. Oops, which one? That's this one. Go to the beginning and go. Okay, so we're understanding now microscopic and macroscopic mass, we already have a very good understanding of it. Here are the learning goals for the next section. You have those written down. How do we get the exact masses, or how do we get these relative masses? We use something called a mass spectrometer. And you don't have to know a ton about, you don't have to know really anything about how the mass spectrometer works, but I'm going to give you just a brief idea. You take a stream of your atoms or molecules or whatever you want, you ionize them, you take some electrons off so they're charged, and then you accelerate them through a magnet, and the magnet, when it reacts with a moving charge, deflects the moving charge. But it deflects it relative to how massive it is. So if you have a small particle that goes through there, it deflects a lot. And if you have a bigger particle that you send in there, it doesn't deflect as much. So you spread things out by their mass. Super handy. That's all you have to know about a mass spectrometer. It spreads things out by their mass. Okay, so you would get two signals, a signal up here for the lighter particle and a signal down here for the heavier particle. And then you could just arrange them. And you could arrange them by relative mass, it turns out, because you can set any one of them to relative mass 1, just take the smallest one, the lightest one, set it to relative mass 1, and then you can calibrate and get the relative masses of everything else in the sample. So if you got relative mass 1 and you put some hydrogen in, you could calibrate that to relative mass 1. That's a hydrogen atom. If you saw something at relative mass 2, then you could say, well, that might be a hydrogen molecule. It would have twice the relative mass. Or it could be a deuterium, the hydrogen isotope. Hydrogen with mass 2. There is a hydrogen of mass 2. So it could be an atom of a different isotope, or it could be the molecule. And you can just kind of continue down here. This mass 3, that could be a hydrogen molecule where one of the hydrogens has mass 1 and the other has mass 2 to give you a total mass of 3, total relative mass of 3. Or it could be a helium with mass 3. Isotope of helium. Or it could be an isotope of hydrogen that has mass 3. It's called tritium. Here's a mass, relative mass 11, 12, 10, 11, 12. That could be carbon atoms. But there's a lot of things that have mass 12. So you don't know for sure, you just know the relative mass. Here's 13. That could be carbon 13. And here's something interesting. So remember we said the ratio of carbon 12s to carbon 13s in nature is about 100 to 1. If you did the experiment with natural carbon, this is what you would see, but the peak heights would be 100 to 1 because there'd be 100 times more 12s than 13s in there. So you can separate out the isotopes and you can see the ratio of isotopes by number. This isn't 100 to 1, that's not the scale. I think there's a homework problem where you do that with aluminum or something. At 16, that could be oxygen. 16, molecules. 18, it could be water that has a hydrogen of mass 1 and an oxygen of mass 16, or it could be the isotope of oxygen that's heavier, oxygen 18. And you can just do this on down the line. Okay, here's oxygen that has two oxygen 16s. Here's oxygen that has an oxygen 16 and an oxygen 18. And here's an oxygen molecule that has two oxygen 18s. So 3 different masses of oxygen. And that's true in the air. This is how we do a lot of our climate science, is the different masses of those particles they settle differently in the atmosphere, and it's how we can, based on the temperature of the atmosphere. So let's talk about this one. Equal relative masses of oxygen. Atomic isotopes are put in a flask like this. What does that mean? That means I put an equal number of oxygen 16 atoms and 18 atoms. If it's an equal relative mass, that's equal number of particles of oxygen 16 and oxygen 18 in a flask, the atoms. And I let them react randomly to form oxygen molecules. And then I take the mass spectrum of that. Let's talk about that one. Everybody, our DAs will spread out, and we'll talk about that. Okay. Wonderful discussions there. Let's see what you're thinking. Touch the screen if you have not yet. A and B are very popular. C is not too popular. And it looks like B is getting more popular as we go. I'll bring in another screen today. The people in the web are watching online don't get to talk to anybody. And even you guys sometimes need some help. So here's an argument for every answer. And here, you don't have to know the answer, but maybe you can figure out from here which of these is the truth, which of these really makes sense. It's another way to think of it. I don't know if I put those. Do we put these in the, is this in your slides? Okay. We could put them there, but the people that said A, and I think you should all say A initially. You should say, well, 16 and 16 can knock into each other, and 16 and 18. So you get one at 32, you get one at 34, and then when 18 and 18 bump into each other, you get one at 36. And it'd be equally likely, you'd think, for all of those things to happen. But statistically, it actually isn't. You could think of it this way, there's two ways for this collision to happen. The 16 could bump into an 18, or an 18 can bump into a 16. There's two ways for that to happen, and there's only one way for an 18 to bump into another 18. And so it does turn out that you get twice as many of this mass as this mass. I don't really care if you knew that part. If you answered A or B, I was thrilled. But the real statistics is the dual combination is just more likely to happen, if you do it randomly. Okay? Oh, cool. All right. Now, the combustion of a hydrocarbon with oxygen yields to the products shown. This is the mass spectrum. So you put a hydrocarbon, and hydrocarbons are compounds that have carbon and hydrogen. I guess that's not too mysterious, is it? These are hydrocarbons. They react with oxygen, and then you take the products and you squirt it into your mass spectrometer, and you get that mass spectrum. What does that mean about which hydrocarbon it was? Holy crap. Can you do that? Talk about that for a couple minutes and see what you think. I'm just gonna climb over stuff. Have I talked to you guys yet? What do you guys think?
Not really sure.
Oh, this one, yeah. Yeah, this one is gonna take a minute. Do you have any ideas? This one, yeah, no, yeah. Yeah, that would help too. Let's start with what you get, what the result is. You get something that has mass 18 and something that has mass 44. So you get two compounds out. Mass 18 sounds suspiciously like water. And we had carbon dioxide on the last slide too. It has relative mass 44. You guys might start with the result, which is you have whatever the reaction has, whatever it produces something that has mass 18 and something that has mass 44 are the products. Yeah. We've already had these on the board like 4 or 5 times. What's something that has mass 18? Water. And so what's something that has mass 44? We had that carbon dioxide. That could be what, you can't be positive that that's what those are in a mass spectrum. All you know is you get those two things with those relative masses. But if you're starting with carbon and hydrogen and oxygen, carbon dioxide and water they have oxygen and carbon and hydrogen in there. So go from there. Science. Okay. A lot of good discussions out there. Now, this is a chem quiz. I walked right up to somebody and said, what do you think? And they're going, well, geez, give me a minute. There's a lot in here, right? So you weren't supposed to get this. And that's true with many chem quizzes. You're just supposed to talk. And even if you only talk about part of it, that's okay. Talk about the part that you get. And then hopefully another neighbor can add to that, or you'll get through that. So let's see what you were thinking. We're all over the board. Ethylene is a little more popular, but lots of votes for acetylene as well. So, that might have been helpful. I'll start putting those up. That'll give you some help. But let's just go through it. Methane reacts with oxygen, and then we kind of guessed that 18 and 44 were water and carbon dioxide. We kind of say that's probably what's produced. In fact, that is the combustion. Combustion of hydrocarbons in oxygen gives you carbon dioxide in water. And that I do want you to know. I will often just say combustion of a hydrocarbon. You need to know that the products are carbon dioxide and water. That makes you an ambassador of science. This one's kind of important. So if you take nothing else home from Chem 1, take home the fact that when you burn hydrocarbons in oxygen, the products are carbon dioxide and water. Okay? That will not be on the exam explicitly, but you'll burn a hydrocarbon, you have to know this part. Okay? So you could just go through, you had 4, you could just, or 3, you could just go through and balance them all. If you balance the number of hydrogens and carbons on both sides, you would see, well, there's 4 hydrogens, there's 1 carbon. But 4 hydrogens make 2 waters. 1 carbon can only make 1 carbon dioxide. So there's twice as many water particles as carbon dioxide particles. Okay? And you can just keep going. What if this is 1 to 4? What if it's 2 to 1? Well, all those hydrogens end up there. So this ratio that says there's the same number of waters as carbon dioxide, well, the same number of waters as carbon dioxide, every single one of those carbons had to be one of those. Every single one of those hydrogens had to be one of those. It's the only place they could have come from. So the ratio of carbon to hydrogen here is the same as the ratio of carbon to hydrogen here. The oxygen doesn't even matter. The oxygen actually just spreads it out for you, so you can see the carbons and the hydrogens. So this says the carbon dioxides have 1 carbon, waters have 2 hydrogens, so it's 1 carbon to 2 hydrogens on both sides. 1 carbon to 2 hydrogens on this side, 1 carbon to 2 hydrogens on this side. Okay? Equal ratios, and if the number of particles is equal, surprisingly, maybe you don't get equal here because the water has twice as many hydrogen particles as the carbon dioxide. So 2 carbons would make 2 carbon dioxides. 2 hydrogens can only make 1 water. So the twice as many carbon dioxide particles as water particles. Okay? Brilliant. Is that what we said? I forget what the question is again. Oh well. Was that the question? Sorry. Oh yeah. Okay. Well, this is the important part. Did you understand that? I forget what the exact question was. Can we go back? What was the question? Sorry. The question was, combustion of a hydrogen yields that. Yes. So if your hydrocarbon yields something that looks like that, that's what it yielded, then that came from something like acetylene. Okay? So that brings up an interesting point. All that mattered was the ratio of carbon to hydrogens. That's all that mattered there. It was the same. You can't lose any carbons or hydrogens. You can't destroy any matter. So every carbon makes it through to the other side. Every hydrogen makes it through to the other side. But that brings up an important point. Every one of these hydrocarbons then, if you burn it and look at the products, every one of these gives you the same mass spectrum because the ratio of carbons to hydrogens are the same. So you could not distinguish between those two by the mass spectrum alone. In this case, we were talking about these particular combinations, but it also could have been this molecule that would have given that same, or this would have given the same mass spectrum as the answer acetylene. So the mass spectrum gives you ratios, but it doesn't give you the exact total molecule. What other piece of information would help? Well, let's say that the reaction didn't go to completion. So there's a little bit of the reactants left, and they show up on the mass spectrometer. Would that allow you to distinguish which of the isotopes it was? You'd have that ratio of carbon dioxide to water, but you'd also have what? What's the other piece of information you'd have? You'd have the reactant in your mass spectrum, and what does the mass spectrum tell you? It tells you the relative mass of the reactant. These have different relative masses, so you could see how massive the reactant was, and you'd say, that relative mass is twice that relative mass. So if you see that big relative mass, you can decide the mass of the reactant on the mass spectrum. You could distinguish between these, okay? These things are called empirical formulas. It's called an empirical formula because if you just the empirical means you do an experiment. The experiment we did gave us only the ratio of carbons to hydrogens. That's the empirical evidence. That's all we had. And from the empirical evidence, all we can say is it's one of these. That's an empirical formula. Any multiple of the empirical formula is possible. So there are a lot of different molecular formulas that have the same ratio, the same empirical formula. Okay, wonderful. We will have an exam Friday evening. It'll be online. It will appear it'll appear two places. It'll appear on the syllabus link. You'll just be able to click that link that says exam on the syllabus. It'll open. It'll also be one of the quizzes. You'll go to your quiz and do that. We'll put that in an announcement so you can do it. It'll look essentially exactly like a homework. It'll just be for credit, okay?
Is it gonna cover like the lecture for material or just like what?
Again, it covers up to where I stopped right there, okay?